Sunday, and so that's coming up. Also, the next Science Sunday, I believe 2 weeks from now, first Sunday in February, we're going to have the engineer that out of college was hired by NASA and worked on the Apollo missions, helped put a man on the moon. So he'll talk about some of his stories. I believe he's got some even artifacts from that time that he was able to come up with. So John Tatro is a friend of his, and John talked to him about coming here, and he agreed. So I think that should be pretty interesting time too. So without any further ado, I'd like to bring Scott up and have him talk about extraterrestrials.
Thank you, Mike.
I checked them all out, they all look like.
No, where you get a room.
I didn't mention anything I was going to mention maybe about what's going on in the other...
Yeah, Darwin Day and whatnot. So, thank you for showing up today. Many of you may have found out about us on Meetup, both the Humanist Meetup group, Humanists of West Suburban Chicagoland, as well as the Chicago Science Field Trips Meetup. And happy to see all of you. Although, to some of you, it may be strange to come to a church to hear talks about science. That's part of the one of the strange ways that Unitarian Universalism manifests itself pretty much throughout the nation, is following a principle of having a free and responsible search for truth and meaning. And to many of us here at this church, as well as frequent visitors, there is no better way to search for truth than the scientific method and scientific discovery. So we thank the church for providing us this space and time to be able to explore this passion for learning. We have a YouTube channel. Some of you are already familiar with that. Our YouTube channel has many of the past several years worth of science lectures. And if you go to our Meetup page, meetup.com, and look for Humanists of West Suburban Chicagoland, you'll find our Meetup page, and there's should be a link in there to our YouTube channel, or just send a message through Meetup, and I will likely respond to you with our YouTube channel. Or you can just search on YouTube, again, for Humanists of West Suburban Chicagoland. All right, that's the advertising bit. So, we began this investigation a while back, talking about vision and color and how light is ubiquitous in the universe. Almost all stars produce what we call visible light. And because of that, we can expect that a sensitivity to visible light would be common in any extraterrestrial organisms, whether they're analogous to plants or animals. So from there, we sort of leaped into a discussion of what can we plausibly consider about alien physiology. You know, what does physics and chemistry tell us about the limitations of a being? For example, they likely have eyes or some kind of photoreceptors. We talked a lot about that. And then last time I talked with you about the Drake equation, which is a sort of a thrown together equation that tries to figure out the probability of other intelligent, communicative, advanced beings elsewhere in the galaxy or in our universe. And today is my final discussion about this topic of interstellar life and aliens, and it's about how do we get there, or how do they get here? It's about interstellar travel. So we're going to need to understand what our potential is for making contact. Another name for this is how to meet new friends in the cosmos. All right, there's 3 or 4 parts to this. I'm going to try and jet through. The first part has to do with the outrageous size of outer space. Now, you can see pictures. This is a picture taken by the Hubble Space Telescope. It's a picture of thousands and thousands of galaxies. Each galaxy is about the same size as our Milky Way galaxy, which has about 100 billion stars. And you can look at this picture and go, oh yeah, I can easily see that I can go from one side of this picture to the other just by moving my gaze a little bit. So, you know, it's really hard, and I might even say that it's impossible to get an intuitive grasp of just how big outer space is. So one of the things I'm going to try to do today is to help you get an appreciation, perhaps a more visceral appreciation for the size of outer space. So let's start by talking about the various journeys that you could take. You could take a journey to the moon, or you could take a journey to Pluto. And by the way, this image of the moon and Pluto is essentially to scale. It's one of the reasons why Pluto is considered a dwarf planet and not one of the major planets of the solar system. As you can see, it is noticeably smaller than Earth's moon. So how long would it take you to get to the moon if you're driving in a car, which can go at about 0.025 kilometers per second? Well, if you were to set off in your speedy Prius, or whatever car you have, you could get to the moon in about 178 days, so you have to pack a lot of munchies. If, however, you wanted to take that same vehicle to Pluto, it would take you about 9,500 years. Well, let's try something faster. Let's get on a jetliner. On a jetliner, which goes 0.25, about 10 times faster, 0.25 kilometers per second.
100 times, no? 10 times.
Yeah.
10 times.
Okay. You can get there in about 18 days, which is, if you'll look at the number above, it's about 10 times the 178. So you can get to the moon in about 18 days on a jumbo jet. Isn't that interesting? And if you wanted to go to Pluto, it would only take you 951 years on a 747. All right, well, let's move up by another order of magnitude. This is, or 2 orders of magnitude, so this is 100 times faster. This is essentially the fastest speed of any space probe that humanity has ever launched into space. And with this fast space probe, you could get to the moon in about 4 hours. It would take you approximately 10 years to get to Pluto, and in fact, that's about how long it took the New Horizons probe to get to Pluto. Now compare that with the speed of light. Now look at this. Light, which travels at about 300,000 kilometers per second, takes only 1 1/3 seconds to get to the moon. That's pretty amazing. And if you wanted to get to Pluto, it would only take you 7 hours. That's a lot faster. And there's a sense in which the speed of light is the fastest you could ever move. Actually, you can never quite get to the speed of light, but we're not going to talk a lot about relativity today. A little bit later on. So here are a couple of images that I created for my ever-pending book. This is an image of the Earth and the moon and the distance between them to scale. This is the size of the moon compared to the Earth. And those little lines underneath the planet Earth and the little line underneath the moon, that's how far each celestial body wiggles back and forth because of the mutual gravitational attraction as they orbit a mutual, what's called the barycenter that I talked about a couple Sundays ago. Anyway, this is the distance between the Earth and the moon to scale. It's pretty far away. Now, here's a similar to scale image, and I apologize, we've had all these dark, dreary days, and today, of course, is bright and sunny, and it's hard to see some of the slides. But this is an image to scale, roughly, of the distance between the Milky Way galaxy and the Andromeda galaxy. This is to scale. So the distance between them is roughly about 20 of the size of these things. And, all right, now, just like that picture, the Hubble Space Telescope picture, when you glance at this picture, you can easily encompass with one gaze and glance the distance between the Milky Way and the Andromeda galaxy. No problem. In fact, I can take a computer drawing and I can draw an arrow between the two, and I can draw that arrow so fast that I can imagine what it would be like to travel to the Andromeda galaxy. But in my book, I recommend an exercise, a little homework exercise to the reader. I say, take a pencil, and you can trace this diagram, or you can even write in a book. Sometimes I write in books. You can write in this book, and I want you to draw a line from the edges of the Milky Way galaxy to the edges of the Andromeda galaxy. And I want you to do that as fast as nature allows a light beam to get from one to the other. All right, so you put your pen down, and here you go. All right, and about 100 years has passed. And now about 1,000 years has passed. I don't have a perfectly steady hand. But let me just cut to the chase. If you were to undertake this exercise to draw a line at light speed to scale on this piece of paper, it would take you 2.5 million years. That's how big outer space is. It's ginormous. So a NASA scientist on Thursday or Friday of this week hopefully released a couple of videos for me. I'm exaggerating. He released these videos and I happened to steal them. And this is a real-time depiction of how fast light moves. This is light traveling around the Earth. As you know, it goes around the Earth about 7.5 times in a second. That's pretty zippy. All right, here's the next video. This is the Earth and the Moon, again to scale, similar to my picture. Let's see how fast light moves between the Earth and the Moon. There you go. That's not bad. That's pretty zippy. Okay? All right, next one is light moving between the Earth and Mars. Here we go. There goes the little blob of light. You see it? Go, 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 go. You can get it. Go. Go. Oh, yes. Yeah. Isn't that something? That's what it would be like to travel at the speed of light to Mars. And that's nowhere. That's close. That's 3 times closer than it is between here and the sun, when Mars is as close to us as it gets. So we got a while to wait. Imagine taking a similar journey to the nearest star. Now, waiting 3 minutes to get to Mars, I mean, that's a little boring, but we could tolerate that. If you wanted to get to the nearest star, traveling along a light beam, it would take you 4.5 years. And that's just the nearest star. And speaking of the nearest star, here it is. Here's a depiction of it. This is Proxima Centauri, and there have been planets discovered around Proxima Centauri. So that's pretty cool. Now, the problem is that the star around Proxima Centauri, the star Proxima Centauri has a planet called Proxima Centauri, I think it's B. And the problem is that planet, in order to be warm enough to support liquid water, orbits so close to its star that flares, let me go back, flares from that star would, you don't really see it, but there's a flare that I animated, but you can't see it because of the bright lights. These flares, which are something that red dwarf stars are prone to do, would sterilize any planet that's close enough to have liquid water with ultraviolet radiation and other sorts of high energy radiation. So maybe that's not such a good place to go. In order to go to a star that has a pretty good chance of having a more hospitable planet, we'd probably have to travel something like 50 light years, so about 10 times more. So instead of only taking 4 years at the speed of light, it would take 50 years or 40 years at the speed of light. 50 years just to go say, is there anything interesting here? Boy, talk about a dead-end career. All right? Also, it would take a lot of rocket fuel. We're going to talk about that in a minute. So, let me give you a little refresher about the speed of light and relativity. I talked about this a few years ago, but just for those of you who are not familiar with it. So, there is a sense at which you are already moving at the speed of light. And everything else in the universe is also moving at the speed of light. You remember, you've probably heard that Einstein specified that space and time are kind of interchangeable. We live in what's called a space-time manifold, right? And physicists have introduced this term called rapidity, which is kind of analogous to speed. And the rapidity with which you traverse space-time is always the speed of light. The question is, are you mostly moving through time, or are you mostly moving through space? You've got to change off one or the other. And here's an example of this. This diagram, this is an arrow. There's a little red arrow here that will show up in a moment. This is essentially standing still, where you're only moving through time and not much moving through space. So, if you put enough energy into increasing your kinetic energy, your energy of motion, then you can move towards moving through moving through space much more rapidly than you move through time. And in fact, from somebody's perspective who is watching you, your time would slow down. Your biological processes would slow down, your wristwatch would slow down, any atomic isotopes that are decaying would decay more slowly from their perspective if they're watching you. So this is one of the strange effects of special relativity theory, is that time seems, and not just seems, it literally does progress at a different relative rate depending upon your relative motion through space, the rate of your motion through space. So you can think of this as a kind of rotation. You're always moving at the same rapidity, that's the length of that red arrow. It's just a matter of whether you're moving through time or you're moving through space. And the fastest thing we've ever made, the space probes that I talked about that moved at about 25 kilometers per second, that is so trifling compared to the speed of light that even something that's moving that fast through space is moving through time at essentially the same speed that you are, relatively speaking, standing still. You can think of the speed of light in some sense as an infinite speed, because as you move faster and faster through space, your movement through time diminishes. And you remember that velocity is distance, a change in distance divided by a change in time. Well, if the change in time approaches zero because your clock stops or comes nearly to a stop as you move close to the speed of light, this means that you can get from here to anywhere else in the universe you want to go as rapidly rapidly in terms of time duration as you wish. There's this misconception that the speed of light prevents us from getting to the edge of the galaxy in less than, say, 20,000 years. And nobody would ever live that long. Nobody would live long enough to get to the edge of the galaxy. However, if you move nearly at the speed of light, your clock on your spaceship, on your wrist, would go so slowly relative to the galaxy that you could easily get from here to the most distant edge of our galaxy within a human lifetime. Now, there's one particularly big caveat to that, and that is it assumes that space is empty. And I'm going to talk more about that in just a moment. All right. How do we get there? Shields up. Space is not empty. These are little pieces of something called the Hypatia stone that fell to Earth. It was discovered in Egypt, hence Hypatia, who was a famous librarian in the Great Library of Alexandria before she was killed in a riot. Anyway, Hypatia stone, it's named in her honor, fell to Earth about 28 million years ago. Now, the reason I show this is because there are little pebble-sized bits of garbage out in outer space. And one little pebble-sized piece of garbage that hits a spaceship that's going thousands of miles per second is like a nuclear weapon hitting a spaceship. Well, maybe we can tone it down a little bit and we can somehow manage to avoid the bigger pieces of rock that are maybe the size of a BB. And maybe, instead of hitting those boulders the size of a BB, maybe we only have to worry about cosmic dust. This is pictures of little micrograins of cosmic dust. Again, apologies for the little bit of washed out colors on the slide. But little bits of cosmic dust. When those hit a spaceship going really fast, those would be like artillery shells. Not only that, this is a picture of a hydrogen atom. I won't go into details about how it's made or how accurate it is, but it's a cool picture, hydrogen atoms. If you're going an appreciable fraction of the speed of light, a hydrogen atom hitting your spaceship would rip right through it like a bomb. So, space, for all of its darkness, is not empty. It's full of different atoms and molecules and bits of dust and tiny little rocks and sometimes big rocks. And avoiding these when you're traveling super fast is going to be really hard. I mean, you can imagine sending out a radar beam ahead of you, which still moves at the speed of light, and it goes out ahead of you, and it says, oh, well, it's too late. Because you've traversed about 1 million miles in that time. So space is not empty, and oh, by the way, as if matter weren't enough, space is also filled with energy. It's a very, very modest energy. It's about 4 degrees Kelvin worth of background microwaves, but it's still energy. And one of the things that happens is if you try to plow through that energy at relativistic speeds, then that energy becomes like a morass of radiation that is bathing your ship in deadly X-rays or gamma rays. So space is not entirely empty, and that's going to impede any attempts at moving near the speed of light. So scientists who work on these sorts of things have said that the fastest that we can hope to go safely is probably about 20% light. And if you're moving at 20% the speed of light, the effects of special relativity that I mentioned a moment ago are essentially negligible, maybe a 3% change in your clock speed and whatnot. So moving at 20% the speed of light is the same kind of physics, essentially, that we would have for things that are moving without considering relativity. So how can we get to such a fast speed? Oh, by the way, this is a picture of, happens to be a nugget of uranium in a cloud chamber. And this is just to illustrate the energy of particles that are being emitted from this little nugget of uranium. But imagine all the cosmic rays that you're hitting faster and faster, just like your windshield hits raindrops faster as you move faster. Imagine all the cosmic rays and the density of those per unit area as you move through space. And those are pretty deadly things, especially to a fragile chemical machine like human body. So we're going to talk a little bit about getting there. How could we possibly get there? Well, rockets. Let's consider rockets.
Yeah, there they are. Coming in like meteors, real fast. You're going to do a final burn here in just a moment.
I can't even see them. Oh,
There's final burn 1 and 2. 2 candles coming down. Double sonic booms. And I see 2 standing. Perfect.
All right, that is one of the coolest things we've ever accomplished as a species. Rockets that go up into space, come back down, and land safely exactly where they're supposed to go. That's amazing technology. So let's talk a little bit more about rockets. Now, this is my ugly slide. I apologize in advance. It's got a lot of numbers on it, some mathematics. So let's pretend we've got a rocket that we want to accelerate to 20% the speed of light. Well, it's got, let's say, about 810,000 times the mass of the ship plus its cargo using rocket fuel. So that 810,000 is a number you can calculate using this little thing called the rocket equation. You can predict how much fuel you'll need for a particular trip at a particular speed with a particular payload. And so whatever your mass of your ship and your cargo is, multiply that by 810,000 to come up with how much fuel you need to get to 20% the speed of light. So we can assume it'll take about, I don't know, let's say 14,000 kilograms of food and water per person times, let's just take 10 people. Let's be modest about it. Take 10 people. That's 140,000 kilograms. Let's say we've got, 500,000 kilograms of spaceship. We're taking all the telescopes and scientific equipment and spare parts and whatnot that we'll need. And then you add those together, and then you multiply that by 810,000 times, and that comes up with this hundreds, thousands, millions, billions, 518 billion kilograms. Not bad. That's 56,470 aircraft carriers. Or nearly 176,000 Saturn V rockets. All right? Well, that's kind of depressing, isn't it? Doesn't look like we're going to be able to do that anytime soon. Now, that's just to get somewhere at 20% the speed of light. If you actually want to stop and do some experiments, you're going to have to double that, essentially. Not quite, because you'll have a little bit less fuel by the time you're there. But anyway, you'll have to double that to stop and look around. Oh, and by the way, if you want to come home again, you'll have to double that entire number again. Yes?
Does the weight of the fuel itself have to be moved back into the calculation?
Yes. Yeah, that's why the doubling is a little bit hokey here, because you will have burned some fuel. But as an order of magnitude estimate, this is valid enough to show you that it is not a viable concept. Yeah. Okay, rockets aren't the answer. What about a nuclear-powered rocket? NASA has actually worked on this. So you send water or some other kind of material that can melt and turn into a gas, you send that through the center of a superheated nuclear reactor, and it comes out the other side as a high-velocity jet of steam or whatever. And this, in principle, could allow you a much greater efficiency than a normal chemical rocket, at least in terms of moving around in the relatively low gravity domain of interplanetary space. But that's not going to take you to the stars, right? It's still infeasible that that kind of propulsion system could get you to the stars. What about lasers and mirrors and solar sails and whatnot? That's a really good idea, and people are working on that too. But that will get you around in the solar system. It's not going to get you anywhere in interstellar travel because sunlight diminishes by the time you get to Neptune and Pluto and perhaps to the point where it's trivial, right? A solar sail will do nothing once you get about beyond Jupiter. So solar sails are nice ideas and probably something we should experiment with in terms of inter-solar system interplanetary travel, but for interstellar travel it's useless. And laser beams, even a laser beam that's columnated when it comes out of the laser will spread out so much that it won't even be able to impart enough light energy to a solar sail to get to a star. Now,
Scott,
yeah.
I'm just wondering, once the main energy drive is to leave our gravity system,
Right.
how much do you need in terms of fuel to keep going from anywhere? Once you get going up to speed, there's no friction, I'd imagine, or very little. So basically, it's maybe running of the spaceship and pumping oxygen into
Right.
things, or
So yeah, once you reach a certain speed, you can just keep, keep going at that speed. Momentum is conserved. But if you want to change course or you want to slow down and look at something, then obviously you're going to have to change your speed again. And you need to expend some kind of energy and probably some kind of reaction, what's called reaction mass, in order to do that. Now, if you already have a spaceship you've built outside of the Earth's strong gravity well, say we build a spaceship at one of the Lagrange points around Earth or something, then the delta V, the change in energy and velocity can be a little lower because you're not having to escape Earth's gravity. You've already done that when you've lifted all the material out. But it's still implausible that we'll be able to impart enough speed with any of these technologies to get something to the stars in a reasonable amount of time. With one caveat, they're looking at microsatellites. So chips, silicon chips, computer chips are getting so capable of doing calculations and measurements and storing data and transmitting data and all of that, that it is conceivable that you could have these little microsatellites that are accelerated on laser beams to reach super high velocity, and then you just shoot them like bullets out into the cosmos and see what happens when they get to nearby stars. But that's not saying anything about human travel, that's just maybe a probe. And it would still take years and years for that data from that probe to get back to Earth because light is slow. So solar sails are not going to work. Back in the late 40s, early 50s, they came up with this idea of a Project Orion, where you would eject your handy nuclear bomb out the back end of your spaceship, and then it would explode and press against these hydraulic plates connected to your spaceship, and it would these impulses would impel your spacecraft forward. Now, that'd be a way to get rid of a lot of the nuclear weapons on Earth. But it's impractical for various reasons, not the least of which is deadly radiation. And besides that, politically, can you imagine the nations of the world saying, "Oh, sure, you can take 5,000 nuclear bombs and put them in orbit"? Yeah, it's all for science. There's another, I think this was Project Icarus, if I'm remembering correctly. There's this idea of an unmanned spacecraft powered by nuclear fusion reactions, little pellets that are expelled out the back and then superheated so that nuclear fusion liberates even more energy. But again, not really all that practical, and certainly not a mechanism for having human beings travel. And then NASA is working on this currently, as we speak, they're working on this small-scale fusion reaction device using some of the latest advances in fusion technology to build a fusion-powered rocket, or at least explore the possibility. But still, these are not going to be able to accelerate enough of a payload to be able to do interstellar travel with any kind of efficiency. And then there's the Bussard ramjet. Some of you read about that in science fiction and perhaps science fact. The idea is you put this giant funnel out in front of you, this big scoop, scoops in hydrogen and gunk that may be out in the non-empty space, and then it accelerates it, kind of like a jet engine accelerates air, and ejects it out the back. So you don't have to carry your fuel with you, you just get it from outer space. Problem is, how do you ionize, if you're going to use a magnetic or electric field to try and guide these particles, how do you create a field strong enough to do that? How do you ionize the particles so that you can guide them with an electric or magnetic field? Just the physics of trying to get a scoop that is miles big to collect enough matter and channel it into your reaction chamber. Nobody has solved those problems, and they may not be practically solvable. But it's a cool idea. All right, let's talk about some ideas for getting there that are some more science fiction oriented. NASA is working on this spaceship concept that could get to Mars in maybe as short as 45 days. So that's a lot less than the 3.5 minutes that light takes to get there, but it's still obviously nowhere near the speed of light. So they've got this prototype idea for using an antimatter drive. You just have to get together about 10 milligrams of positrons needed to get humans to Mars. And they think that the cost of collecting that those positrons and whatnot, and manufacturing them and storing them and all that, they think they could build this kind of rocket for about $250 million. So that's in the realm of cheaper than a wall. Which is a unit of measure these days. So that's not a bad idea. This is the positron engine. Right? You got the hot bleed and the cold. It looks a lot like a nuclear furnace. And then you've got your storage unit over here. So storing a tiny bit of antimatter, manufacturing a tiny bit of antimatter, that's plausible. But to manufacture enough antimatter to get us to the stars, we don't have the first clue how we could do that. The amount of energy it would take to run particle accelerators to create even a pound of antimatter is mind-boggling, right? More energy than the entire budget of humanity would have to go into just creating antimatter. Now, the great thing about antimatter is that it is the most compact and efficient mechanism for storing potential energy known to science. But strangely enough, and this is strange, it's a whole different topic, strangely enough, there doesn't seem to be much antimatter in the universe, so we'd have to make it. And making antimatter is very hard and very expensive. Okay, but let's say we do it. We spend a few $1,000 worth of money and make enough antimatter to get us to the closest star. Well, how do you store it? Storing the thing about antimatter is when it comes into contact with, a glass tumbler or a steel containment vessel or a person, immediately disintegrates into gamma rays. Well, that's a little unhealthy. So how do you make it? How do you store it? How do you use it to generate enough thrust? We don't have any good answers to that, even speculatively. So antimatter rockets, not likely to happen. All right, wormholes. Everybody's favorite, right? Carl Sagan approached Kip Thorne, one of the leading scientists, about general relativity. And general relativity has to do with the shape of space-time. I talked about the space-time manifold. Well, general relativity gives us a set of formulas for calculating how matter and the shape of space-time are related to one another. Matter and energy and pressure and all these things. And these equations, this specification of general relativity has proved to be astoundingly accurate. It predicted gravity waves, among other things, and they were found to really exist. So we're pretty confident that general relativity is a pretty accurate representation of the way the universe really works. Well, one of the ways you can fiddle with the equations of general relativity is that you can say, instead of going from here to there, you just poke a hole through space-time in higher dimensions, and that way, instead of taking the long way, you can just take the short way. That's a valid solution to Einstein's general relativity equations. The complications, unfortunately, are things like they may be infinitesimally short-lived. It may take an infinite amount of energy to open them. They may release a catastrophic amount of energy when they're created, and maybe you have to go to the end point first to set up the other end of a wormhole. And oh, by the way, if you try to get close to a black hole, which would be the sort of nucleus of a wormhole, if you try to get too close to a black hole, you're going to be shredded and ripped and torn apart and irradiated and killed in all kinds of unpleasant ways. But, I don't know, maybe? I doubt it. All right.
Question?
Yeah.
Actually, there was a paper that was recently written by some folks who are saying that it might actually be possible to enter gently into the event horizon of a black hole. It may not be as violently devastating as we picture it to be. So, yeah, who knows?
Yeah. Well, so as you get larger and larger black holes, as you get to the galactic-sized black holes with millions or billions of solar masses, then the tidal force, you've heard of spaghettification, you get too close to a black hole and it rips you to shreds. The tidal forces around a galactic-sized black hole would be mild enough that you could cross the event horizon without any deleterious effects, without having a lot of stresses and strain on your molecules and even your physiology. So that is certainly plausible that if you get a big enough black hole that you could at least go into it, you could start your journey into it without dying, but after that, boy, things get dicey pretty soon. And nobody really knows what goes on beyond the event horizon. That's a whole other wonderful topic. And it's pure speculation at this point. So another idea, a few years ago there was this idea that you could fire some microwaves in a cone-shaped cylinder, and the microwaves bouncing off the wall and bouncing off one end would impart less momentum or more momentum than the ones going straight out the back, so you could have a net transfer of forward momentum. Except that physics and the equations don't really work out that way. Conservation of momentum doesn't allow for that kind of drive to work, and there have purportedly been prototypes built that fail miserably. You can account for the minuscule forces that seem to be manifest on these chambers by simple thermodynamic stresses and strains vis-a-vis the support apparatus and whatnot. So that doesn't seem to be going anywhere, literally. And both of those I just talked about, that magnetron is what's called a closed system drive, where just by it's essentially pulling yourself up by your bootstraps, and physics just doesn't allow that, just like it doesn't allow perpetual motion machines. But there are other open system drives. There's this idea of spooling out a long wire conductor tether, and that whipping around in a magnetic field could generate electric current, and then you could use that electric current to power something that would maybe ionize some material and then shoot the ions out the back of your capsule, so you could grab energy from a local magnetic field. Maybe, right? But again, not scalable to the point where we could tap the galactic magnetic field to create anything plausible in terms of an interstellar drive. Gravity assist. This is another kind of open system where it relies on the gravitational field you can see this little probe here. I'm sorry, again, it's hard to see. You can see this probe that got slingshotted around a planet, and it accelerates a little bit when it gets close to that planet. It steals a little bit of the momentum of the planet, poor planet, so that the probe can jet off into space. But you need to have something that can gravitationally assist you, and there's not a lot of, as far as we know, huge masses that we can plot out on our trajectory between here and the nearest star. There's speculative quantum mechanics gobbledygook about the Casimir effect and zero-point energy and whatnot. You'll read about some of these in science fiction. But again, none of that violates the conservation of energy when you look at it in detail. And even if you can get some energy by charged plates coming together because of this quantum mechanical effect, you still have to exert energy to separate them again so that you can get a tiny bit more energy once they collapse again, like clapping your hands. So again, all speculative, but it's just not going anywhere. All right, this is a really cool idea. This was they came up with this idea back in the 70s, this Mexican physicist. They're not all bad. Alcubierre. Am I saying that right, Mike? Do you know? Okay, so he has this idea for a warp drive. And his idea is that you can warp space, pile it up behind you in general relativity. You can warp space to a big wave behind you and then press it down into a pit in front of you with this spaceship. And at the edges of your spaceship, the strength, the tidal forces of this would just be astronomical. So you want to have a really strong structural material there, but then you can live safely here in this middle region. And NASA has actually given us a picture of what this might look like. Looks pretty, doesn't it? Alcubierre Drive. Oh, this is gorgeous. How about that? I know. Here it is scaled up. Right? Wonderful, wonderful idea. Except in order to create that, you need negative matter. Not antimatter, negative mass. Anybody have any handy? Nobody's ever found anything like negative mass. All right, just somebody knows particle physics. We're all baryonic matter. Even antimatter is regular mass, energy. Right? You need negative energy. So there's no, even though the equations of general relativity say that you can kind of surf this wave traveling in a spaceship, there's no plausible mechanism for actually building it. And oh, by the way, the cool thing about the Alcubierre Drive is that you don't actually move through space-time. So it gets over the idea, it gets around the idea of getting from here to there by taking the space-time that's here and making that space-time there, right? It's in that sense, it's appropriate to call it a warp drive because it's like surfing a wave of space-time. You can make space-time, you know about the expansion of the universe, and the expansion of the universe during the inflationary period was, in some sense, faster than the speed of light. That's because nothing can go faster than light. And by nothing, I also mean space-time. So space-time itself the metric of space-time can expand or warp without any constraint on how rapidly that happens. So this Alcubierre Drive could theoretically move the space that an object occupies faster than the speed of light would be able to. Sean Carroll, a theoretical cosmologist who I think is one of the sharpest and best most articulate theoretical physicists that's around today, says this when speculating about dark energy and general relativity and its relation to the Alcubierre Drive. The Alcubierre warp drive is a very interesting arena for thought experiments to try and better understand general relativity and quantum field theory, but it should give you zero hope for actually building a spaceship someday. In short, it requires negative energy densities which can't be strictly disproven, but are probably unrealistic. The total amount of energy is likely to be equivalent to the mass energy of an astrophysical body, if you were to be able to do it, so that you would need a star's worth of mass to do it. And the gravitational fields produced would likely rip any ship to shreds. This is Sean Carroll, my personal estimate of the likelihood we will ever be able to build a warp drive on this model is much less than 1%. And the chances it will happen in the next 100 years, I would put it less than 0.01%. So as a physicist, he's got to make everything numeric. Yeah, it might take an infinite amount of energy or negative energy, maybe just as much energy as exists in the universe, maybe not an infinite amount. Maybe it would cause an immediate explosion of radiation, similar to Hawking radiation when a black hole evaporates at the very end. And how do you control the warp bubble that's ahead of you if that space is moving out faster than the speed of light? You can't send a signal. You can't manipulate any device that's... I don't know. Not going to happen. But it's pretty. Okay, cryogenic stasis. These are people in here. We can't freeze humans without causing cells to rupture. We've been able to freeze goldfish, and that's about it, and bring them back. What about low metabolism stasis or hibernation? Well, maybe, but for years? Would you still age? Your metabolism doesn't stop. And who would deal with emergencies? How long does it take to wake you up and put you back to sleep? Right? This is maybe, but not likely. And then we have this beautiful idea of generation ships. You build this gigantic structure that can support people. Oh, by the way, it's been estimated that to have a genetically viable seed population of humans, you need about 10,000 individuals without being in the position where you've got all kinds of deleterious mutations and inbreeding. So you build a spaceship big enough to have 10,000 people on it, and you put a little terrarium in it. I don't know where it's getting its light, but whatever. And you send this out as a city in space to visit the stars, and you have to be really good at recycling because there's no way station, there's no pit stop, right? You have to take everything you're ever going to need, and your children are going to need, and your grandchildren, and your great... You're going to have to take everything a population of humanity needs along with you for the ride. And, you know, it can be entertaining, it can be a big party, right? I mean, there you are with 10,000 of your closest friends. Except, boy, space is really boring, right? What are you going to do? I mean, you can create music and artwork and whatnot, but it's going to get really boring. And, oh, by the way, how are you going to limit it to 10,000 people? If your spaceship has a capacity for 10,000, let's just say 11,000 people, if you really pack them into janitor closets and whatnot, how are you going to make sure that over many generations your population stays at 10,000 people? And what about people who are pro-life? What about people who ascribe to religious beliefs that say you should not tamper with human reproduction, right? How are you going to make sure that you've got people out there that maybe your initial 10,000 are perfectly fine with some kind of birth control, but what about their children? What if they dig into an old book and say, oh, wait, we shouldn't be doing this, right? What if half the crew decides they want to go somewhere else? Limited resources, and the boredom that sets in. You're looking out the window, here you are on your way to the nearest star, and it's going to take you 500 years. Look, I can see the sun. It's a tiny little glimmering dot. And your grandchildren, hey, look, I can see the sun. It's just boring, right? What about the resources that you're going to need? Where are you going to get the resources? Where are you going to get the food, the water, the titanium to make nifty new iPhones? Right? Where are you going to get all that stuff? You don't have a whole planet at your disposal.
We have one generation ship, right? It's called the Earth, and it has all the problems you talked about.
That's right. Oh, I'm not bored yet, though, I tell you that. All right, what about the fact that things break? Have you ever seen a machine that could run for more than 100 years with moving parts? Yeah. Some people might be able to make it, But imagine a turbine or an actuator on one of those fancy doors in Star Trek. After about 400,000 duty cycles, you think that's still working? Right? You get moving parts in a thing, and those parts are going to wear down. Probably in a generation or two. A lot less than hundreds of years.
Now you have something to do.
Well, that's true. We're not bored anymore. We're dying! All right. Circuits fail. Gamma rays, cosmic rays, all these things affect microcircuits and whatnot. It's just not very hospitable out there. And think about interpersonal conflict, you know, the reds versus the blues. You know, I hinted at this later. Maybe you get a bunch of, you know, peaceniks as your first 10,000, but human variation, what happens by the third generation? You're going to get zealots, and you're going to get, you know, ingrates, and you're going to get iconoclasts, and all other kinds of variability. And are they going to get along, packed into a sardine can that's lost among the stars? I doubt it. All right, here's my favorite view of a spaceship. So you do something like a generation ship that's here among these rings. So you spin these rings to get 1 g of gravity, and then you move at a very modest pace, and you put all your business and your nuclear reactors and whatnot way out here where it's relatively safe, and you've got a big shield to protect you from cosmic ne'er-do-wells. And, you know, maybe this could take thousands of years to get there, but it's still, I mean, it's pretty and it's better than no idea, but it's still a bad idea because all those other problems are still there. I mean, it'd be kind of cool. You think about living in this ring and you've got cities, and would you get slums? Would you have class warfare? What happens when you get so many people together? All right, part 3. Where is everybody? Last part of the lecture. If this is possible, if somehow all of these challenges that I've laid out in front of you can be surmounted, and we just aren't smart enough to have discovered a way around all of these problems, then maybe somebody somewhere has figured it out. So, they should be out there. There's this guy, Enrico Fermi, one of the most brilliant polymaths in terms of his ability to think about science and make analogies and ask penetrating but often simple questions. Enrico Fermi said, look, there are billions of sun-like stars in our galaxy. Many of them are older than the sun. Many of those likely have Earth-like planets. We know that they do now. Earth-like being where liquid water can exist and they're not too heavy and whatnot. Well, assume that they evolve intelligent technological life. Okay. Assume distant stars can be populated at 1 star for every 10,000 years. Talk about a generation ship. 10,000 years to get to a new star and populate it. Even so, the galaxy should be awash with these beings. It only takes a few million years at the rate of 10,000 years per population event. It only takes a few million years to populate the whole galaxy. So where are they? Possible answers. Intelligent technological life is extremely rare. I've talked about the eukaryotic cell, right? Won't go into detail, but life existed on our planet for 2 billion years before an archaea and a bacteria decided to live peacefully and happily together as a unified organism, right? 2 billion years and trillions and trillions and trillions of microorganisms during that 2 billion years. And maybe just one time, an archaea and a bacteria decided to cohabitate. That, we have no idea. We only have a population sample of 1. We have no idea how common that will be in other biomes. It's very likely that the laws of physics and chemistry and geochemistry have conspired to make it possible for primitive life like bacteria and archaea to exist on other worlds. Very plausible. Complex life, where you engineer with structure rather than chemistry, which is what eukaryotic multicellular organisms do, the probability of that We don't know, but it may be very low. Called a big filter event. Maybe interstellar travel is impossible. Maybe whatever we try to do, it'll just crash and burn, like all the things I've talked about up until now. Maybe it just isn't possible. And then there's this. All right, this is a philosophical bit. It's one of my favorite things to think about. What if we had no fossil fuels on this planet? What if we had evolved in a paradigm where there were not, in our history, shallow oceans full of microbes and water plants that were able to turn into coal and oil? What if that contingency had never occurred on our planet, but everything else is the same? Could we build rocket ships using steam engines? Right? Would we ever mine, would we build machines capable of extracting enough uranium from the world to put it in centrifuges and make fuel-grade uranium stockpiles? Right? Without fossil fuels to bootstrap, maybe this isn't possible. It's one of my pet philosophical ideas. But if you do have fossil fuels, is climate change a trap that confronts every civilization? Right? It's just basic physics. Greenhouse warming will happen anywhere in the universe that these elements of liberating CO2 in terms of fuel into the atmosphere, that will happen wherever you are, whatever planet you're on. And then, oh, by the way, there are other things like diseases and environmental catastrophes. What are the chances of surviving that long enough to get out into space? Right? So here's one of the ideas that I'm in favor of, because I think it's more plausible, is that we will construct intelligent entities that go out into space. So evolved life, like us, will get to the point where we can create intelligent, sentient beings, like Mr. Data or whatever from Star Trek, that don't have the biological limitations for food and water and such fragility as our biological selves. This might be plausible. We have so far to go in terms of artificial intelligence that we don't even know what kind of limits might exist in that domain yet. And then there's the idea of potentially uploading your personality. Right? Just yesterday I was reading about a brain scan technology that it's 1,000 times faster than previous technologies. So is it plausible that someday you could take the chemistry and the electricity that manifests you, your consciousness, right? I'm a monist, I think there is only one you, and it's all chemical. Could you take that and copy that into some kind of simulation that runs on a computer? Maybe. All kinds of wonderful science fiction have been written about that. And I think that's not completely implausible. Maybe these intelligent entities could be in the form of space probes or spacefaring beings, constructed beings, that can self-replicate. Right? They can improve on themselves generation after generation. There's a wonderful science fiction set of books called the Bobiverse, about this guy named Bob, who gets uploaded into a machine and goes out to explore the universe and replicates himself. I recommend it. It's really, really good. And it's the scientific fidelity in it is good enough to be, entertaining and not terribly distracting with its implausibility. These are called von Neumann probes. They just go out and they explore. Now, here's the thing about von Neumann probes. If all they need is a source of matter and energy, what the hell do they care about a biologically habitable planet other than as a curiosity? Right? If you can get all the minerals you need out of an asteroid, and you can get all the energy you need from uranium scattered near supernovas, or stars, nearby stars, whatever, if you can get all that stuff that you need, then, other than being just genuinely curious about what the universe has to offer in terms of Darwinian evolution, you don't have to go to a planet in order to be self-perpetuating. So So that's one of the ideas about why there isn't anybody around. There's this idea called the zoo idea, that in order to get sophisticated enough that we can leave our planet and live among the stars as either some kind of constructed or evolved beings, we have to pass through certain gates, and some of those gates involve being able to work and play well with others. Right? Well, if you've already passed through that gate, then you come on to a new species. If they haven't achieved that level of equanimity and pacifism, then maybe you just leave them alone. Right? So maybe they're out there and maybe they don't want to have anything to do with us. Or maybe that's the zoo hypothesis. There they are looking at us. And, well, that's interesting. Don't touch. Or maybe they're everywhere and they're interested in things that we can't conceive of yet. The galactic black hole at the center of our galaxy would be the universe's most astonishing physics laboratory. Maybe there's one of these constructed beings, a whole population of them, somewhere around our central galactic black hole, doing physics experiments and figuring out whether wormholes are possible and extracting energy from the black hole. Who knows? But they might be more interested in that than they would in some backwater yellow star with messy and warlike biology. Okay, interstellar space is vast, cold, dark, lonely, monotonous, and hostile. It's very cold. It's colder than it is today. By the way, trying to get a machine to work today could be problematic. Imagine trying to get a machine to work when it's minus 240 degrees centigrade. All right? There's not many constructed materials that can be mechanically robust at such cold temperatures. It's cold, it's dark, it's lonely. It's empty enough to be boring, but full enough to be deadly. Oh, talk about a conundrum. Given what we know, there's no plausible way we human beings can travel to the stars. It is unfathomably expensive in terms of material, labor, and energy. We're probably either alone or too immature to be relevant to anybody else. Or, it very well could be, you know, that eukaryotic thing where it was really rare, it could be there's nobody else around, at least in our galaxy. Okay, activation energy. A couple graphs. I showed you an equation. Here's a couple graphs to wrap things up. Activation energy. Maybe there's some desired state we want to get to where we're exploring the universe, but to get there, we're going to have to overcome a tremendous technology or energy barrier. Right? In chemistry, that's called the activation energy. To get to a desired location or state, end state, you have to put a lot of effort into the system, a lot of energy into the system. And maybe there's all kinds of these barriers that are, in some sense, insurmountable, or at least today are insurmountable. Speaking of graphs, often you hear that we're on this exponential trajectory, right? There will be a singularity of artificial intelligence, so it's exponential growth in the capabilities of technology. This is a lie. Anytime you ever hear about some system that is undergoing exponential growth, it's a lie. You know what's really happening? This is really happening. This is called a logistic curve or a sigmoid curve. This means it can look a lot like exponential growth when you're down in here, but eventually something stops you. Right? Population growth. Right? There's a carrying capacity of our planet, etc. And interestingly enough, we can have these stacked on top of each other. Right? We used to think that the human, Malthus back in the 1700s, thought that we would come to a point where the Earth wouldn't have enough food to support a larger population. Then what did we do? We started using fossil fuels to create the energy required for agriculture. Wow, we're off and running again, right? But you can also think about this as speed. You know, there's horses and buggies, and then there's steam engines, and then there's cars, and then there's jet planes. You can have an arbitrarily large number of these logistic curves stacked up together, and it can approximate an exponential curve. But at some point, there is a limit to what you can do, how fast you can go, how capable and competent your machines can be. And we don't always know what those limits are. We know one of them, the speed of light. Okay, thinking about these things, it makes me think about the big questions, like, why do we explore? And if we had dominion over the stars, what would we do with them? It makes me think that perhaps we are the caretakers of our galaxy. Mostly, it makes me think about how precious and rare each one of us is. That we should take care of our planet, lest we deprive the galaxy of wondrous wanderers. We might be the caretakers of our galaxy. We are certainly the caretakers of one another. If you want to find intelligent life, creative and wonderful beings,
just look around here on Earth.
all right, thank you.
We have some questions? Very well covered, thank you.
Thank you.
It's so full, it's hard to come up with thoughts. Thank you.
Have you thought about what the appropriate role is between public efforts as opposed to private efforts when it comes to, maybe not getting to the stars, it's maybe just pie in the sky, but in terms of planetary expeditions, that sort of thing? Because, I'm of the generation where everything was NASA, right, government, that sort of thing, but it seems like that may be starting to change. How realistic is it to think that private enterprise could accomplish more perhaps than we can even imagine?
Well, you know that activation energy thing I showed, those humps? I believe that one of the primary roles of government, of a well-functioning society, is to help overcome those humps. And once you've overcome that hump, then it becomes much more plausible that private industry can play a role, right? Like the internet and GPS and Velcro. I mean, so many technologies that we leverage today happen because somebody invested in the money. Let me give you a really great example. You remember this brouhaha over, what was it, Solar One or whatever during the Obama years, this solar energy company that went belly up? The government had invested a lot of money in it and whatnot. You know what the government also invested in with that same program? Tesla, right? So the government, one of the roles of government is as the spender of first resort, right? If you've got a challenging project that is too risky for private industry, you've got to have a collective social program, government program, in order to get it off the ground sometimes. So I think that private industry can play a role once these technologies are well defined, but government has to break down the doors. Any question?
Yeah, hi Scott, I think that was great. I'd just like to add an extra number to the possibility of antimatter drives, because at Fermilab, we made more antiprotons than anywhere else and stored them, like 10 to the 13 per day, right? 10 trillion antiprotons per day stored, and we used many megawatts to do that. If you collected all those antiprotons that you make in a year and annihilated them, 100% efficiency, you could light a 100-watt bulb up for a few seconds. I mean, that's the amount of energy.
Right.
I mean, because it's micro, you're using a huge,
Yeah.
and of course you've got to keep the antimatter away from touching matter, otherwise,
Right.
So, and CERN made a few anti-atoms, and we were doing that, but a few atoms is not going to get you very far.
Right. Thank you.
I was thinking too about the experiment that went on in the deserts of Arizona, where they put something like seven volunteers inside the what was it called? Biosphere, yeah. Where they put 7 volunteers in, and then they actually had to cheat the system to make it work, and they were sneaking in supplies and things.
Yeah.
it never, you know, in a short amount of time, that did not perform very well for folks. You know, and here you have to have something that your whole life depends on it, on some interstellar travel.
And there's nobody to help you. And you can't communicate with Earth in any meaningful way, because it could take years for a signal to go, hello, well, and then everybody dies.
You can say goodbyes about it.
Right.
One question that I had, Scott, was, and that one of the reactions you could have to your excellent talk is, why bother? Why are we even bothering to look at some of these things, you know, that appear to be impossible and require too much energy? Could you speak for a minute why we should bother?
Well, part of it is because I have not ruled out, and as far as I know, most people haven't ruled out interplanetary travel. You know, Mars and Titan and Mercury and many moons in the solar system. These are all very interesting places, and we may be able to plausibly develop a human presence there. That's one reason. Another is, if we didn't think about these things, we wouldn't know what's possible and impossible, right? So, next, in March, I will likely give a talk about, I'm transitioning into a topic called a scientific disposition. And one of the things I'm going to talk about is the importance of humility, and another is the importance of honesty, right? Honesty, science is the best tool we have to keep us honest about what's real and possible. And if we don't continue these explorations by asking what if and why not, then we've given up the fight. But I think another conclusion is, like I said at the very end, it should highlight how precious we are and how much it incentivizes us to keep care of one another and our planet.
I think the second answer to that is, if we weren't curious, we would still be fire, air, earth, and water.
Yeah, right.
So that it is our curiosity which just drives all this stuff. Again, the idea that the atmosphere itself, and Mike did this, the atmosphere itself is made up of different components. We didn't know that.
Right.
Until someone put a frog or whatever inside of a bell jar and the damn thing died.
Right. Well, the speed of light, right?
Exactly.
You know, 200 years ago, 150 years ago, people thought we can go as fast as we want, as far as we want, and then we came up against this hard wall of the speed of light. Nobody wanted that, but that's reality. So, if we don't keep pushing up against what's true and possible, we're not going to learn our own limitations.
There's no argument for traveling there. You don't have to travel there, we can find out.
Yeah, we can use telescopes. I'm sure you're going to talk a little bit about that in your talk.
Scott, this may be a little off topic, but recently came across, there have been some sort of waves of
Gravity waves?
radiation that have come from deep space. And apparently, they've been coming for some time.
The fast radio bursters, is that?
Yeah.
Yeah.
Is that,
So, have we detected alien signals?
yeah.
Right?
That's what
No. The short answer is no. Long answer is, every time we think we might be onto something, somebody says, oh, that's a neutron star, or that's a black hole, or that's an active galactic nucleus, or something, or a supernova of a very peculiar type, right? Every time we've ever thought that that might be a cool signal from an alien, it turns out that it's just a star showing off.
One type of possible energy source that you didn't mention during your talk was that could do almost 100% conversion, is essentially if we had the ability to have our own, let's say, private black hole.
Right.
So you don't need matter, antimatter.
Oh, you're right. Black holes are the most efficient energy generating machines in the universe. 50% efficiency. Far more than any other thing except matter, antimatter, right? But there's none close to us, which is good and bad, you know.
If you were, again, what they call Kardashev, if you were a civilization that could harness,
Yeah,
you
the Kardashian.
possibly could create your own black hole. That's
Right.
a different discussion.
yeah.
What's effect? Is that the Kardashian?
No, Kardashian scale.
That's a little different than I'm thinking.
Kardashian.
Kardashev. I think it's Kardashev. something like that. Yeah, the Kardashev 1 can harvest essentially the energy of a star. Kardashev 2 can harvest the energy of a
Kardashev 1 is energy of a planet, 2 is energy of a star.
3 is,
a galaxy.
yeah. And then most of us are some logarithmic fraction along the way. Right? Anyway, interesting but not very useful idea.
Well, yeah, about black holes. Now, people think black holes radiate. Hawking said they radiate, but actually, a black hole the mass of the Earth is colder than the microwave background it's sitting in, and will not radiate. It will actually accumulate energy. It has to be much lighter than the Earth, and like, I forget, 100 tons or something like that, to actually be hotter than the microwave background, and therefore to radiate. Now, if you could catch one of these black holes from space, and put it in orbit around the Earth,
And feed it.
you could actually feed it with the rubbish, put rubbish in, and keep it at the right temperature, like 1,000,000 degrees, going round, and then you've got a perfect, first catch a black hole, right?
And then move it.
And then, get it in orbit around the Earth, and then throw rubbish into it, and great.
Yes, an arbitrarily sized spinning black hole, you can extract energy with an efficiency of about 50%. And we think most black holes should be spinning because most astronomical objects are spinning. So it's called a Kerr black hole. All right.
Very nice. Thank you so much.